Example 4, it is night. Someone who is 6 feet tall is walking away from a street light at a rate of 3 feet per second. The street light is 15 feet tall. The person casts a shadow on the ground in front of them. How fast is the length of the shadow growing when the person is 7 feet from the street light? How fast is the tip of the shadow moving at this instant? Okay, so once again, we're going to sketch the situation here. So we've got a street lamp, which is 15 feet tall, and we're assuming that the height of the street lamp doesn't change. So the street lamp is 15 feet tall. And you've got a person who's 6 feet tall. Once again, we're going to assume that the person's height doesn't change. Okay, so that's the person there. They say that the person is walking at 3 feet per second, and they don't mention that it changes, so we're just going to assume that that's a constant. So this is 3 feet per second walking, and so then the light casts a shadow. So we're going to go ahead and have the light casting a shadow down that way. And so if you've ever experienced this as you're walking away from a light, the length of the shadow is going to change. The closer you are to the light, the shorter the shadow is, the further away you are, the longer the shadow. So the length of the shadow and the distance from the light are what's changing with time. So to be consistent here, I'm just going to look back. So P is the distance from the person to the light, to the street light, and then S is the length of the shadow. So we're going to be consistent with that. We're going to call this P, the distance from the person to the street light, and S is going to be the length of the shadow. And we're going to assume that the ground is level like that. Maybe you're like in a level parking lot or something. So we can take advantage of some right triangle trigonometry. So the question is, how fast is the length of the shadow growing when the person is 7 feet from the street light? Okay, so how fast is the length of the shadow growing? So S represents the length of the shadow. So how fast that's growing is a dSdt. So they're looking for a dSdt when the person is 7 feet from the street lamp. So that's when P is 7 feet. So that's the instant that they're interested in. Now the 3 feet per second is how fast the person is walking. So that's going to be our rate of change dp dt. So we need to look at a relationship between the two things that are changing here with respect to time, P and S. That's going to be true for all time. And the relationship we're going to use is the so-called similar triangle relationship. Because both the big triangle and the little triangle share common angles, theta, 90, and then the complement of theta, whatever that is up there. So if I look at the ratio of opposite over adjacent, aka the tangent, that's going to be the same ratio regardless of which triangle I'm looking at. So in the big triangle here, the opposite side is 15 feet tall, and the adjacent side is the P plus the S, feet long. In the smaller triangle, the opposite side is 6 feet tall, and the adjacent side is S feet along. And so using similar triangles, aka the tangent function, S divided by 6, adjacent over opposite, so S feet divided by 6 feet, oops, put this up there, is going to be the same ratio as P plus S feet divided by 15 feet. Okay. Now we can clear the fractions out by multiplying through by, let's see, let's not do this yet because we want to keep the units there. So we can clear the denominator by multiplying through both sides by 30 feet. So here the feet would cancel. I'd be left with a 5s feet equals a 2p plus 2s. Both of these are measured in feet. And so I'm going to get 3s measured in feet is equal to 2p. That's the relationship between s and p. And this is true for all time. Okay. So now I've related the two variables. Now I'm going to relate the rates by taking the derivative of both sides with respect to time. And we've got constant multiple rules. 3 times the derivative of s with respect to t, which we'll write as ds dt. 2 times the derivative of p with respect to t, dp dt. And so this is our related rate equation. Now notice this is true for all time. And notice that there's no dependence here on s or p. I mean, so the rates are just always going to be this way. So even though we're given dp dt, to solve for just ds dt, I don't need that piece of information. I just need to know what, oh, excuse me, they tell us when p is 7. We don't need this information at all. We just need to know what dp dt is, which is 3 feet per second. Oops, what happened here? Yep. So dp dt is 3 feet per second. So I plug that in. 3 ds dt is 2 times 3 feet per second. So I can cancel 3 off both sides. I get ds dt is 2 feet per second. Now the fact that this is a positive number means that the length of the shadow is increasing. So, and this is the length that's increasing for all time. So in particular, when the person is 7 feet away from the street light, the length of the shadow is, since we've got a positive there, increasing at a rate of 2 feet per second. Okay, so that's how fast the shadow is lengthening. Now they ask us another question as well. How fast is the tip of the shadow moving at this instant? So you got to think of these rates here. The person itself is moving at 3 feet per second. The length that the shadow is increasing is 2 feet per second. So if I want to know how fast the tip is moving, well, the shadow is getting longer at a length of 2 feet per second. The person creating the shadow is moving in the same direction at 3 feet per second. So how fast is the tip of the shadow moving at this instant? We're just going to add those rates to give us 5 feet per second. So that'll do it for example 4.